The experience of physical exercise varies dramatically from one individual to another. Some people complete a short run and find themselves gasping for breath, struggling to recover from what feels like an overwhelming ordeal. Others cover the same distance with apparent ease, their breathing steady and their demeanor relaxed, as though the activity required minimal exertion. While conventional wisdom attributes these differences primarily to factors like cardiovascular conditioning, muscular development, and overall fitness levels, emerging research suggests that the story is considerably more complex. Scientists have begun uncovering evidence that the brain plays a surprisingly significant role in determining how difficult physical activity feels to any given person. This discovery opens up fascinating possibilities for helping individuals overcome one of the most common barriers to regular exercise: the perception that physical activity is simply too hard, too uncomfortable, or too demanding to maintain as a consistent habit. If researchers can develop methods to reduce the sensation of effort without actually decreasing the intensity of the workout, they may be able to help millions of people establish and sustain healthier, more active lifestyles. The fundamental issue lies in understanding that physical effort exists on two distinct levels. From a purely mechanical perspective, effort can be quantified by measuring oxygen consumption, heart rate elevation, muscle fiber recruitment, and energy expenditure. These are objective, measurable phenomena that reflect the actual physiological work being performed by the body. However, the subjective experience of that same effort represents something entirely different. This perceptual dimension of exertion is shaped by complex interactions between sensory information from the muscles and joints, neural processing in the brain, psychological factors, and previous experiences with similar activities. This distinction between objective physical work and subjective perceived effort matters tremendously when it comes to exercise adherence. People do not make decisions about whether to continue exercising based solely on what their bodies are objectively accomplishing. Instead, they respond to how the activity feels in the moment. When a workout feels overwhelmingly difficult or unpleasant, individuals naturally develop an aversion to repeating that experience. They begin finding excuses to skip sessions, gradually reduce the frequency of their workouts, or abandon their exercise routines altogether. Conversely, when physical activity feels manageable and perhaps even enjoyable, people are far more likely to maintain consistent participation over time. The relationship between perceived effort and exercise behavior has prompted researchers to ask whether it might be possible to manipulate the sensation of difficulty during physical activity. Could there be techniques that alter how hard exercise feels without necessarily changing the actual physiological demands of the workout? If such methods exist, they could represent powerful tools for helping sedentary individuals overcome their initial resistance to becoming more active. Research teams at academic institutions in Canada and France have been investigating precisely this question through an innovative approach involving mechanical vibration applied to specific tendons in the body. Scientists specializing in kinesiology and physical activity have designed experiments to test whether stimulating tendons with carefully controlled vibrations might reduce the perceived effort associated with exercise, thereby making physical activity feel easier, even when the body is working just as hard or even harder than usual. The experimental protocol developed by these researchers involves using a wearable device capable of delivering precisely calibrated vibrations to selected tendons. In their initial studies, they focused on two key areas: the Achilles tendon at the back of the ankle and the tendons surrounding the knee joint. These locations were chosen because they connect to major muscle groups heavily involved in cycling and many other forms of exercise. To test their hypothesis, the research team recruited volunteers who agreed to participate in controlled laboratory experiments. Each participant engaged in cycling sessions on stationary bicycles under carefully monitored conditions. The experimental design required each person to complete 2 separate sessions. In one session, volunteers received tendon vibration treatment before beginning to cycle. In the other session, which served as a control condition, participants cycled without receiving any vibration beforehand. During the vibration sessions, researchers secured the vibrating device to the participants' Achilles tendons and knee tendons. The device remained active for 10 minutes, delivering steady mechanical vibrations to these areas before any cycling began. After this preparatory vibration period ended, participants mounted the stationary bicycles and began pedaling. They were instructed to maintain their cycling effort at either a moderate or vigorous intensity level, adjusting their pace to match what they personally perceived as the target effort level. Importantly, the participants themselves controlled the intensity based entirely on their subjective sense of how hard they were working. The results revealed something remarkable and unexpected. When participants had received tendon vibration before cycling, they spontaneously produced significantly more mechanical power output compared to sessions without prior vibration. Physiological measurements confirmed that their bodies were indeed working harder, as evidenced by elevated heart rates during the post-vibration cycling sessions. Yet despite these objective indicators of increased physical work, the participants did not report experiencing any increase in perceived effort. In other words, their bodies were objectively performing more demanding exercise, but the activity did not feel any harder to them. This counterintuitive finding challenges conventional assumptions about the relationship between physical work and perceived difficulty. Under normal circumstances, we would expect that increasing power output and elevating heart rate would necessarily result in exercise feeling more strenuous. The fact that tendon vibration appeared to decouple these normally linked phenomena suggests that the brain's assessment of effort can be manipulated in ways that diverge from the actual physiological demands being placed on the body. Understanding the mechanisms underlying this effect has become a central focus of the research. While scientists have not yet completely elucidated all the biological processes involved, they have developed several plausible explanations based on what is known about how the nervous system processes information from muscles and tendons. One key factor involves the way vibration influences neural activity in the spinal cord. Sensory receptors throughout the musculoskeletal system constantly send information to the central nervous system about muscle length, tension, joint position, and movement. These signals travel through peripheral nerves to the spinal cord, where they undergo initial processing before being relayed to higher brain centers. Mechanical vibration appears to modulate the activity of neurons within the spinal cord itself, potentially either exciting or inhibiting specific neural populations depending on the characteristics of the vibration being applied, including its amplitude and frequency. Another important consideration involves specialized sensory structures called neuromuscular spindles, which are embedded within muscle tissue. These spindles function as highly sensitive stretch receptors that monitor changes in muscle length and the rate at which muscles are being stretched or contracted. Under normal circumstances, neuromuscular spindles provide the brain with continuous updates about muscle state and movement. However, when muscles and their associated tendons are exposed to prolonged vibration, the responsiveness of these spindle receptors changes. They begin sending altered signals to the brain, providing modified information about what the muscles are doing. By changing the nature of the sensory information flowing from the periphery to the central nervous system, tendon vibration appears to reshape the brain's interpretation of physical activity. The brain constructs its sense of effort by integrating multiple streams of information, including signals from muscles, tendons, joints, the cardiovascular system, and metabolic sensors. When some of these input streams are modified through vibration, the brain's overall assessment of how hard the body is working shifts accordingly. The result is that exercise can feel substantially easier, even though the muscles continue generating significant force and the cardiovascular system continues working at elevated levels. While these initial findings hold considerable promise, researchers emphasize that the work remains in preliminary stages. The experiments conducted so far have examined only brief cycling sessions lasting just a few minutes, performed under carefully controlled laboratory conditions. These short-duration tests do not necessarily predict how tendon vibration would perform during longer, more demanding activities like distance running, competitive cycling events, or endurance challenges. The technique has not yet been validated for real-world applications or extended exercise sessions. Scientists involved in this research program have outlined an ambitious agenda for future investigations. Their next priority involves examining brain activity more directly during exercise to better understand how tendon vibration influences neural processing in real time. They plan to employ sophisticated neuroimaging technologies that can monitor brain function while people engage in physical activity. These tools will allow researchers to observe which brain regions become more or less active during exercise with and without tendon vibration, potentially revealing the specific neural circuits responsible for the altered perception of effort. The research program also encompasses investigation of the opposite side of the equation. Just as the team seeks to understand how to reduce perceived effort, they are equally interested in understanding how factors like pain, discomfort, and fatigue amplify the sensation of difficulty during exercise. Many people struggle with physical activity, not only because of inherent exertion, but because of pain from injuries, chronic conditions, or simple muscle soreness. By understanding how these negative factors intensify the feeling that exercise is too hard, researchers hope to develop comprehensive strategies that address multiple barriers to physical activity simultaneously. The broader vision driving this research extends well beyond academic curiosity about neural mechanisms. The ultimate goal involves developing practical interventions that can help sedentary populations overcome their resistance to exercise and adopt more active lifestyles. Physical inactivity represents one of the most significant public health challenges facing modern societies. Sedentary behavior contributes to numerous chronic diseases, including cardiovascular disease, diabetes, obesity, and various forms of cancer. Despite widespread awareness of exercise benefits, vast numbers of people remain persistently inactive, often citing difficulty, discomfort, or lack of enjoyment as primary reasons for avoiding physical activity. If researchers can create evidence-based techniques that genuinely reduce perceived effort during exercise, they may be able to help inactive individuals successfully navigate the challenging initial phases of becoming more active. The early weeks and months of a new exercise program often prove most difficult, as previously sedentary people confront unfamiliar sensations of exertion and discomfort. Strategies that make this transition period feel more manageable could dramatically improve the likelihood that newcomers to exercise will persist long enough to experience the positive adaptations that naturally occur with regular training. The research also touches on fundamental questions about motivation and the psychology of physical activity. The brain evaluates exercise not simply in terms of momentary difficulty, but also in relation to perceived benefits and rewards. People make implicit cost-benefit calculations when deciding whether to engage in physical activity, weighing the discomfort and effort required against the anticipated rewards of improved health, enhanced appearance, better mood, or other valued outcomes. By improving understanding of how the brain performs these evaluations, scientists hope to identify leverage points where interventions might tip the balance toward choosing activity over inactivity. The importance of regular physical activity for overall health and well-being cannot be overstated. Exercise influences virtually every system in the human body, supporting cardiovascular health, maintaining metabolic function, preserving cognitive abilities, regulating mood, strengthening bones, and supporting healthy immune function. Yet despite this overwhelming evidence, translating knowledge about exercise benefits into actual behavioral change remains notoriously difficult. Novel approaches based on neuroscience and the understanding of perceived effort may finally provide new pathways for addressing this persistent challenge. As this research continues to evolve, it may eventually yield practical applications that extend far beyond laboratory settings. Wearable devices capable of delivering therapeutic vibration could potentially become tools for personal use, helping individuals make their workouts feel more comfortable and sustainable. Rehabilitation programs might incorporate vibration protocols to help patients recovering from illness or injury re-establish physical activity patterns. Athletic training programs could explore whether these techniques might help athletes push through difficult training sessions more effectively. The emerging science of perceived effort represents a paradigm shift in how we think about exercise and physical activity. Rather than focusing exclusively on building physical capacity through progressive training, this approach recognizes that the psychological and neurological dimensions of exertion deserve equal attention. By learning to manipulate how exercise feels, researchers may unlock powerful new strategies for helping people overcome one of the most common and persistent barriers to healthy, active living.